Okay. So they were kind enough to give me a laser, which you can see is nice green laser. Life is good. You've got a green laser. This is a diffraction grating. My children, oh, this would be good up here. It fell. Let's see. There. How's that? Can you hear me? Okay? Yeah. All right. Good. This is a diffraction grating. My grandchildren procured these to watch fireworks, and it turns white light into rainbows. And it works because there are many fine lines drawn in here, 18,500 per inch, and they are drawn both vertically and horizontally. Now, if I take my laser and I shine it through the diffraction grating, I get that. Why? Because it's a laser. And that's a good enough answer, isn't it? Oh, that's a laser. That's why. So, what's happening here is that the laser light is passing through all those thin lines, and it's separating into a bunch of wave fronts. Yeah, the laser light is made of waves, and as those waves pass through the lines, it creates a whole bunch of many different wave fronts, and those wave fronts interfere with each other. What you're looking at there is an interference pattern, and it interferes constructively where you see a dot, and it interferes destructively everywhere else. So a nice, pleasant interference pattern. But now I'm going to take my laser here and I'm going to turn the intensity down, way, way down. So far down that the laser can only fire 1 photon per second. Remember that light is made up of particles, and those particles have discrete amounts of energy. So it is possible to reduce the brightness of the laser until it's firing 1 photon per second. Now let's say that you could see 1 photon hitting the screen. So here I'm going to take my 1 photon per second laser, and I'm going to pass the single photons through my diffraction grating. What will I see on the screen? Will I see an interference pattern? I cannot see more than 1 dot per photon, because the photon must deposit its energy at a single point. That is the definition of a particle. So I must see on the screen a dot for every photon. But what we do see is that the dot will be here, and then here, and then here, and here, and here, and here. The dots will appear all over the screen in a random order. But if you add up all those dots, if you were to take a camera and open up the shutter and just allow the camera to watch the screen for an hour, it would collect 3,600 dots. And then when you developed the film, that's what you would see. The dots appear in the same place with the same frequency. Notice how some of them are bright and some of them are dim. That's just because more dots are appearing in the center. Fewer dots are appearing on the outside. Now that is an interference pattern. So the interference pattern must be there even when it's a single photon. The single photon must be passing through the diffraction grating, separating into a whole bunch of waves. All those waves must be painting an interference pattern on the screen, but not one you can see. And then the photon must deposit its energy at a place where the interference pattern is brightest. And it does this somehow randomly, because you cannot predict from moment to moment where the dot will appear. Which means this pattern here is actually a pattern of probabilities. It shows you the probability that a photon will land in the middle or that the photon will land at the outside. The brightness of each dot is the probability that the photon will land in that spot, which means the interference pattern is a pattern of probabilities, which means the waves are waves of probabilities. And that hurts my brain, so I'm going to stop talking about it. The talk I'm going to give you is a talk I've given many places and many times. It is called Expecting Professionalism. And before I begin it, let me introduce myself slightly. My name is Bob. I've been a programmer for about 50 years. I wrote my first line of code, if you could call it code, in 1964. My mother had purchased for me a small plastic computer. This computer had 3 flip-flops, 3 bits. They were little plastic things that slid back and forth. They had a 1 and a 0 painted on them. 3 bits. It had 6 AND gates. These AND gates were metal rods. The metal rods had springs that would pull them towards the flip-flops, and there were slots in the flip-flops that the metal rods could fall into. If the metal rod fell into the slots on the flip-flops, it could engage a mechanism that would change the state of one of the flip-flops. It was a 3-bit finite state machine. But you could program it. You could program it by slipping little soda straw tubes, short little stubby soda straws, onto pegs on the flip-flops that could block the AND gate rods from activating the device. And so you were able to program it to count from 0 up to 7, the most you can do with 3 bits. There would be another program that would allow it to count down from 7 to 0 and then back to 7 again. Another program allowed it to add 2 bits, yielding a sum bit and a carry bit, a true full adder. And there were many other programs that you could put into this machine. I found this frustrating because the manual that came with the book did not tell you how to program it. It just showed you what programs you could put into it. And I had to put those programs in without understanding them, and that bothered me. At the end of the manual, there was a little paragraph. The little paragraph said, if you want the advanced programming manual, send in $1 and a stamped self-addressed envelope, and we will send you the advanced programming manual. So I stuck $1 in an envelope, and I gave them a stamped self-addressed envelope, and I mailed it into them, and 6 weeks later, it came to me. 6 weeks, because we didn't have Amazon in those days. I opened it up, and inside there was this little booklet. I still have this booklet. I keep it in a plastic Ziploc bag. And I opened it up recently, and I read it. It is perhaps the most competent definition of Boolean algebra written for a 12-year-old that I have ever seen. It has perhaps 20 pages. And in those 20 pages, it outlined the basics of Boolean algebra, starting with Boolean variables, Venn diagrams, Carnot maps, associatives and distributive property, De Morgan's theorem. And after you've walked through all of that, it said, okay, now that you know how to do a little Boolean algebra, here's how you program your machine. You write down the truth table of how you want the bits to change. You convert that truth table into a set of Boolean equations. You use the tools of Boolean algebra to reduce those equations to lowest terms, and then here's a little table that will tell you from those equations where to put the pegs, the tubes on the pegs. I had a little program in mind. It was called Mr. Patterson's Computerized Gate. I wrote down the truth table. I converted it into Boolean equations. I reduced the Boolean equations to lowest terms. I put the tubes on the peg. I cycled the machine, and that machine did exactly what I wanted it to do. And I was a programmer. That was it. I had made the machine my slave. I was its master. I was the god of the machine. I felt the power. I was a programmer, and I've never wanted to be anything else since. This probably happened for you. There came a moment in your life when maybe you were in a store somewhere and you walked up to a Commodore 64 or a Radio Shack computer and you typed a little basic program that just printed your name infinitely. And you went, "Yes, I am the God!" And you wanted to be a programmer from that point on. Many of us wanted to be programmers because we felt the power of making the machine do your bidding. We have a problem, you and I. How many of you are programmers? So this is most of you. Good. Some of you aren't. Somewhat suspicious. We have a problem. This problem is that we do not have a profession. We have, I'm not sure what to call it. What is it? A job, a task, but there are no ethics. We have never defined ethics to our job. We have never defined a set of practices or disciplines. We cannot say that we have a profession because there is nothing that we profess. And this is a problem because we rule the world. We didn't know this, we didn't want it, but it has become true. You and I, programmers, we rule the world. Other people think they rule the world, but then they write the rules down and they give them to us. And we code the rules into the machines that make our civilization work. Our society depends now for its existence on computers. Everything happens inside of computers. Every significant commercial transaction, any significant law that is passed, any kind of traffic on the streets, any kind of air traffic in the air, anything that happens in our society happens through the agency of a computer. And we are the ones controlling those computers. How often does a person in our society interact with a piece of software? And I'm not talking about technical people. I'm talking about grandmothers. How often do grandmothers interact with pieces of software? And the answer to that is probably once a second. Anytime they use their phone, anytime they look at their watch, anytime they use a microwave oven or a dishwasher, anytime they get into their car. How much code is in a car? 100 million lines of code in a modern car. 100 million lines of code in a modern car. And you guys, that should scare the heck out of you. Because you know. My wife has a car, it's got a front-looking camera. And it can recognize the lane markings on the road. And so it will identify if you're in the appropriate lane position. And if you drift out of the lane, like you're falling asleep, it will tug the wheel back. The software controls the steering wheel. What will it do on February 29th? Have they tested that? How many people have died in cars because software failed? Many. The answer is many. Toyota just paid out a big penalty because a whole bunch of people died in their cars. And the reason that people died is because some poor software guy didn't calculate the size of an internal stack properly, and every once in a great while the internal process blew the stack and corrupted a piece of memory that belonged to a process that controlled both the brake and the accelerator. And the cars would accelerate into trees. A number of people have been killed by software. And so we have to come to grips with the fact that we are killing people. We didn't get into this business to kill people. We got into this business to print our name infinitely on the screen. But we are killing people. And society does not quite recognize this yet. Not quite yet. We don't quite recognize it yet. Society does not quite understand just how important we are. But they're beginning to learn. Even a few years ago, software developers became fairly notorious. When's the first time a software developer appeared as a major character in a Hollywood film? Jurassic Park. Dennis Nedry. And he was the villain. We had, by 1990, whatever that year was, sometime in the 90s, software developers had become, society had become aware enough of us to name us as a villain. Which is interesting. I was in Stockholm last year, visiting the guys at Mojang. You know, the guys who did Minecraft? And I gave them a lecture, and that was fun, and then we went out for beer. And we were sitting in a lovely little beer garden, middle of Stockholm, surrounded by a fence, and we're just chatting and drinking beer, and up walks this kid, this kid runs up. And he points at one of the programmers who happens to have red hair. Some of you may know this guy. His name is Jeb. If you track the Minecraft world, Jeb is somebody who's well known. And this kid walks up and says, "Are you Jeb?" And Jeb kind of nods and says, "Yes, I am." And "Can I have your autograph?" And Jeb writes his, because it happens to him all the time. He writes his autograph. Our children have begun to see software developers as heroes. From villains to heroes. There are children alive today who are 10 years old who aspire to be programmers. That's an amazing thought. But we achieved the pinnacle a few weeks ago, when the CEO of Volkswagen testified before Congress, and Congress asked him why was this nasty code, this lying, cheating code, put into these cars, and the CEO of Volkswagen America said, "Well, we really don't know. It was just some software developers who did it for whatever reason." Now, that was a stupid thing for him to say, and it was perfectly transparent. On the other hand, it signifies something very interesting. We have graduated to the status of scapegoat. CEOs can now tell the world it was our fault. And here's the thing about that. There were software developers who put their fingers on those keyboards and wrote that code that lied and cheated. Software developers did that. And we should be offended. You and I should be offended that those software developers dishonored us in that way. We don't have an ethical structure yet that would allow us to do anything about it. But we should be able to do something about it. We should be able to say, those programmers cannot be programmers anymore. They have stepped outside. They are no longer programmers in good standing. They have violated the ethical contract that we have with our users. There will come a moment, probably not very long from now, when some poor programmer is going to do something stupid. and it'll kill 10,000 people. And you could imagine it. It's not that hard to imagine, right? What, driven by software, could kill 10,000 people? Name a bunch of things. There's a lot. Some poor software guy is going to kill 10,000 people, and the world will react. Society will react and say, hey, this can't go on. And the politicians of the world will rise up in righteous indignation, as they should, and they will point their finger squarely at us. You'd think they'd go for our bosses, but they won't. They'll go right to us because it was our fingers on the keyboard. And they will ask us the question, how could you have let this happen? And we better have an answer for them. Because if our answer is, well, you know, my boss said I had to do it and we had a deadline and so I did it. If that's the answer, then the politicians of the world will do the one thing they're good at. They're not actually very good at it. They will legislate. They will pass laws. And they will tell us what programming languages we can use and what processes we have to follow, what books we have to read, what signatures we have to get, what platforms are appropriate for us, and we will all end up working for the government. This is something I would like to avoid. And to avoid it, we will have to do what other professions have done in the past. Professions like doctors and lawyers and architects, who managed to establish a set of ethics and a set of disciplines before government got to them. If we can do that, if we can get there before the government does, then when the disaster occurs, and the disaster will occur, and the politicians will rise up in righteous indignation, and they will point their fingers at us because 10,000 people died. But if we can say this was not due to our negligence, because here are our disciplines, here's the standards we follow, here's how we enforce those standards, this was an accident or it was malfeasance, but it was not our industry that is at fault. And if we can say that, we might be able to bypass the worst of what the politicians will do to us. So, what would these standards be like? What kind of ethical principles should we follow? I'm going to transport you to a world where I am your new CTO. Don't worry, I'll let you out of that world soon enough. But for the moment, assume that I am your new CTO. I'm going to tell you what I expect of you. And you will hear these expectations, and your brain will react two ways at the same time. The normal part of your brain will say, perfectly reasonable, good expectation. The programmer part of your brain will react by thinking I'm completely insane. Watch what happens. First expectation. I expect that we will not ship shit. This is a perfectly reasonable expectation. But I see the little smirky smile. I know what everybody's thinking. Oh, yeah, well. Sometimes, you know. So, I'll state the principle. We will not, as a matter of ethics, we will not knowingly ship code that is defective or substandard. And this is not something that you have to get permission to do. You do not have to ask your boss, is it okay if I don't ship shit today? Because you were hired because of your knowledge. You were hired because you know how to ship good code. So you don't have to ask for permission. This is expected of you. And it is not expected, quite frankly, that you would do this in order to meet a schedule or to yield to pressure. That is not expected. No one expects you to violate a basic standard of work. You may think otherwise, but ask them. You don't expect me to ship shit to you. This principle is really just saying, do a good job. Do a good job. Every day, do a good job. And you know what a good job is. You know what it looks like. You know what good code looks like. You know what code that works looks like. Do a good job. When you go home, you should be able to look in the mirror and say, I did a good job today. You won't have to take a shower. Sometimes we go home and we feel, and we have to take a shower. I expect that we will always be ready. What does that mean? You guys doing Agile? You're all supposed to nod now. Oh, of course we're doing Agile. Yeah, we're doing it. Yeah, we're doing it. So, what is your iteration size? Your sprint. What's your sprint length?
2 or 3 weeks.
2 or 3 weeks, which is the traditional answer. 2 is better than 3. And what is supposed to be done every 2 weeks? What is the status of your work at the end of a 2-week sprint?
Done.
Done is an interesting word, because in our world we have decided that done is not a Boolean variable. We have decided that it has a range of possibilities. How done exactly do you want it, sir? Is it done or is it done? Deployable is the word. Every week or 2 weeks, whatever your cycle size is, the code should be deployable. That does not mean that you will deploy it. It just means that you are satisfied, you as a team are satisfied that the quality of the code is deployable. The business may decide that they don't want to deploy it because it doesn't have enough features. For example, log out might work great, but you can't log in yet. Business might decide they don't want to deploy that. But you are perfectly happy deploying it because log out works great. We'll get to log in next sprint. But log out works. And it's been tested and QA'd and documented, and it's all ready to go. And that's what is supposed to be done every sprint. This is what it means to always be ready. To always be ready at the end of every development cycle, where there are very short development cycles, so that you are always ready. I don't want anybody saying, well, you know, we wrote a whole bunch of code, but you know what we should really do now is run it for a month and watch it. And maybe if it doesn't crash after that, then maybe it'll be safe. Has anybody done that one? Stabilization phase? We should just run it for a while. You know, because God knows what'll happen. That's crazy talk, right? We should know. Code should be well enough put together so that you know. I expect stable productivity. Stable productivity. How many of you have worked on a greenfield project? No code, right? You just start with a blank screen, no code. How fast can you go when there's no code? Somebody asks you for a feature, right? And you say, I can get that feature done in a week. And they say, no, nobody's ever done it in a week. Yeah, I can do it in a week. You start writing code, and code pours out of every orifice of your body. And a week later, it's all done. And everybody's going, no, you couldn't get that done in a week. Holy cow, we've never seen anybody go that fast before. Can you do it again? Yes! Come back to that team a year later. Hey, can you do another feature for us? Ooh, tricky. I think it'll take us 6 months. We used to be able to do this in a week. Yeah, but you don't know how complicated this system has gotten. Like, you know, man, if we touch it over here, why it might break over there? In fact, we can't tell what'll happen if we touch a line of code. Like, anything could happen. So yeah, 6 months, you know, because we don't know. That's a problem. And it's a problem that affects lots and lots of software teams. Because they start out fast and then they make a huge mess going very, very fast, and they wind up a year later going very, very slow. And imagine the business who started by seeing them go fast and decided to lay their plans based on that productivity. And all of a sudden the productivity goes down into the toilet, and the business is stuck there going, what the hell happened? How come we're all going so slow now? You're not the same programmers we hired a year ago. Yeah, we are. We're really the same. Well, you're not going as fast as you used to. Well, we're working just as hard, except now we're working hard moving around all this mess we made. I don't want you to do that. I expect stable productivity, which means you will work, you will produce features just as fast a year from now as you produce them today. You will not slow down based on the mess you made, because you're not going to make the mess. How many of you have been slowed down by bad code? Look around. This is everybody, except for the few people who have their hands down, and they're either not programmers or they're liars. Everyone has been slowed down by bad code. Everybody has been slowed down significantly by bad code. And then the question is, why did you write it? Why would you write it if you know you're going to get slowed down by it? And the answer to that is, well, we wrote it because we had to go really fast. I'm going to leave you to deal with the logical conundrum there. There's obviously an issue with thinking clearly. Right? You will slow yourself down by writing bad code. You will slow everybody down by writing bad code. And as long as that bad code is in there, anybody who gets near it will be slowed down. And if the whole system is bad, everybody's going to go slow all the time. I don't expect that. I want you all to go fast all the time, so keep the mess out of the code. Oh, we can't clean the code, it's a mess. Well, then you're going to go slow. I expect inexpensive adaptability. What do I mean by this? I mean that the software ought to be easy to change. The business should not find it expensive to adapt the system to new requirements. It should be easy to change the code. The word software begins with the word soft, and soft means easy to change. We call it software because it was designed to be easy to change. The reason we invented software is so that we could change the behavior of machines easily. To the extent that we have made our systems hard to change, we have turned them from software into hardware. This thwarts the very concept of software. Software is supposed to be simple to change. So I expect the software to always be easy to change. That is just a fundamental goal of your job. Keep it soft. I expect continuous improvement. And what does that mean? It means the software gets better with time. The code gets cleaner with time. The designs improve with time. Every system should be getting better and better, not worse and worse. This is what humans do. Humans make things better, right? We see things that are bad and we improve them. It's human nature. Our software systems somehow violate that. They get worse and worse with time. That's wrong. You and I should be making our systems better every time we touch them. There's a rule, it's called the Boy Scout rule. It's a simple rule. Every time you check in a module, you check it in cleaner than when you checked it out. Real simple idea. Right? Never check anything in worse. Always check things in a little bit better. You check out a module, you have to do something to it, don't make it dirty. And then do some random act of kindness to it to make it a little better than it was when you checked it out. Always check it in a little better and everything will improve. Just that. If we did just that, our code would get better and better over time. I expect fearless competence. fearless. How many of you have brought code up on a screen? And you look at that code, say, oh, it's a little ugly, I should clean it. And your next thought is, I'm not touching it. Because you know if you touch it, you will break it. And if you break it, it's yours. So you walk away. That's not going to be me. I'm not going to be the one. That's a fear reaction. You fear what you created. And if you fear it, you cannot clean it. If you cannot clean it, the only thing that can happen to it is that it must rot. It must get worse and worse and worse. Why does code keep getting worse and worse and worse? Because we fear. Remember when you got your first bit of code to work, the joy you felt at being the master over that computer, and how you wanted that feeling again. Oh, I'm going to be a programmer and make these machines work. You ruled it, and now it rules you. It's all changed around. You fear what you have created. You've lost control of it out of this fear. It now controls you. It dominates you. You react to it. You no longer are the master. What do we do about this? Because it's completely unacceptable. It is the hallmark of unprofessionalism and sheer irresponsibility to have lost control of the thing we created to the extent that we fear any action towards it. What do we do about this? Well, imagine that you had a button you could push. A little magic button. You push this button and some lights blink, and shortly thereafter there's a little ding, ding, and a green light lights up. And that green light means that everything works. And you trust it. You trust the green light. Everything works. Now look at your screen. There's code on that screen. It's dirty. And you think, oh, I should clean this code. And your next thought is, well, maybe I'll just change that one little variable. I'll change that one little variable. Its name is wrong. I'll give it a better name. Hit the button. Ah, green. Ha, worked. Okay, this function's a little big. Maybe I should split it into two functions. Hit the button. Ah, green, good. Okay, this function should probably be moved over to that module over there. Hit the button. Red, oh no, put it back. Oh, I see, I did it a little wrong. Okay, move it over here. Hit the button, green. Ah. If you had that button, you could clean the code. If you could clean the code, then the code would always get better. If the code always got better, you could make it easy to change. If you could make it easy to change, you could go fast. That button is the key to everything. How do you get that button? Where can you buy it? Where do you get that button from? How many of you are practicing test-driven development? Ooh, look at this. We got not quite 10%, and we do have a little of this going on. Test-driven development. Test-driven development is a discipline. A discipline, the goal of which is to give you that button. If you were practicing test-driven development from the beginning, from the start of your career, every system you would ever work upon would have had that button. To start practicing test-driven development now is going to be difficult because you have systems that don't have tests and weren't designed to be tested, and so writing tests for them will be difficult. But that's not to say that it's impossible, and that's not to say it's a bad goal, just difficult. It may take you some time to get that button. But now think of what that button can do for you, what it can do for your team, what it can do for your company. And it makes it almost absolutely imperative to get that button. What is the right level of code coverage? Test coverage. When you run tests, what percent of the code should be covered by those tests?
100.
It's the only reasonable answer. 100%. It's also an unachievable answer. You can't ever get to 100%. But we are used to asymptotic goals. Goals that you always approach but never quite get. Have you ever tried losing weight? No? Asymptotic goal. But it doesn't mean you stop trying. Right? You keep pushing that number higher and higher, 95%, 96%, 96.5%. You get it high enough so that when that green light goes on, you are willing to trust the green light. Has anybody got a test suite where you're on it, and it passes, and everybody kind of goes, yeah, because you know there are things that weren't tested. You know there are big gaps in the test suite. And so the fact that the test passes does not change your behavior. You can make no reasonable decision based on your test suite passing. And that makes the passing useless. When the test suite fails, it at least tells you that something went wrong. But when it passes, it tells you nothing. That's bad. The passing of the test suite should change your behavior. It should allow you to make certain decisions that you would not make otherwise. If you have that button, you wind up with extreme quality, and I expect extreme quality. I expect that the software is going to work consistently, release after release after release. I don't expect lots of problems and crashes and troubles and data corruptions. I don't expect those things. I expect the software to generally work pretty well. An occasional bug every once in a while is probably unavoidable, but when they occur, I expect you to track them down and get them solved and work on them appropriately. Anybody using a bug tracking system? You got one? Maybe Jira or one of them. There's lots of them out there, right? And we take all of our bugs and we put them into a database so that we can track them. I want you to consider what it implies that we have to have an automated database to track our defects. We must have a lot of them if we need an automated system to track our defects. Where did we ever get the idea that that was normal or right? That it's okay for us to have, well, there's only 10,000 defects in the database. Where did we get that idea? How long should the defect list be? It should fit on an index card. It should be small. You should have a little pile of cards. There's 5 or 6 defects in the system. Well, we'll clean them up. Extreme quality. I expect that we will not dump on QA. Do we have any QA people in the room here? Any testers? Oh, got one. Good. Does this look familiar? Waiting for the load to be delivered?
Pretty much what I look at every day.
And you know, the load doesn't come on time, does it? The development team does not deliver on time. Does that change the delivery date? No. So the QA folks wind up under the most pressure. They have the most stress. They have the least flexibility. It is a high-stress, tedious job, and this is how we're going to guarantee quality. There's something wrong with that whole concept. I don't want the software... I'm going to get rid of that because it's ugly. I don't want the software team dumping their load on QA so the QA can sweep all the bugs back to them. You don't just say, well, why don't we give it to QA and they can debug it. When you release it to QA, QA should find nothing. I expect that QA will find nothing. Now, of course, QA will find things from time to time. And when they do, I expect the development organization to react and go, well, how the hell did that happen? And to plug whatever leak that was. Because generally, QA should go through its actions and then report, no defects. How did we ever get to the idea that it was a good thing that QA got defects? Where did that happen? Why do we have QA in the first place? Original software development teams didn't have QA departments. How did we get them? What would motivate the companies of the world to create wholly new departments under different management to make sure that software developers did their jobs? What motivated them was software developers weren't doing their jobs. We were shipping shit. And to come back at that, to deal with that, the companies of the world had to say, well, what are we going to do? These guys are shipping shit. Well, we need to come up with some group that can smell it. How do you reward QA? How do you know if they're doing a good job? They find bugs. The more bugs they find, the more of their job they're doing. The one who finds the most bugs is obviously doing the best job. So now we've made bugs a good thing. There are people now who value bugs. We want more bugs. We want more bugs. Now, the developers. Do the developers value the bugs? There's an old rule in software. It goes like this. If the code doesn't have to work, I can meet any deadline you set for me. Name the date, I will deliver, so long as it doesn't have to work. So now, these two groups, QA and development, both value the bugs, and both can set up a little economy. How many bugs are you going to give me this week? I need a little bit more because I need something on my salary review coming up. Oh yeah, well, I got a deadline to meet, so probably ought to be able to give you 5 or 6 more. Actually, the words are never spoken. No one ever says anything. But the economy exists because everyone understands there's a mutual benefit. And an organization where that is going on is a truly sick organization. Deep disease in there. I expect all of the testing to be automated. There's some exception to that rule, which I'll talk about in a little while, but the vast majority of testing will be automated. The hands you're looking at here are the hands of a QA manager for a large internet travel company. This guy is holding out to me the table of contents for his manual test plan. It is not the test plan itself, it is just the table of contents. He has 80,000 manual tests that he must run every 6 weeks. He ships them over to an army of people in India. Costs him I did. We lose the battery? Something happened. Oh. Hello? So where was I? Army of... He ships them over to an army of people in India. It costs him $1 million every 6 weeks. $1 million every 6 weeks. And he's holding it out to me because the year is 2008 and the financial crisis has begun. And he's just gotten back from his boss's office, and his boss has just gotten back from the CFO's office, and the CFO said, I'm cutting your budget by 50%, there's this big recession on. And he's holding this out to me saying, which half of these tests should I not run? And I told him, well, you can cut the document this way or that way. It doesn't matter. You're not going to know if half of your system works. This is the inevitable outcome of manual testing. Manual testing always ends with you losing the tests. You could lose them directly, like this guy did, because they simply got too expensive. But more commonly, you lose them by QA deciding not to run them because they don't have time. So QA will decide which tests are the most important to run and which are the least important, and you will lose the tests anyway. Manual testing always results in this. And manual testing is insane because we're programmers. We know how to automate. Why wouldn't we automate that? Why wouldn't we have automated tests that test every business rule in the system, every interaction in the system? Why wouldn't we have written those tests? And you think, well, it's expensive to write tests. No, that's expensive. That's people. And look at what we're asking those people to do. Has anybody done this job? Anybody seen a manual test plan? And then you know what you have to do, right? You open this massive book. Enter P9523 into the username field. Enter XX952 into the password field. Click login. Did the welcome screen come up? And this is your job. I don't want QA acting like a bunch of automatons running a program that a computer could write. QA are intelligent, creative people. We should move them away from the back end of the process where they're frankly pretty useless and move them to the front of the process where they can apply creative energy to figuring out what tests ought to be run. And they don't have to run those tests. Programmers ought to run those tests. Mostly those tests ought to be automated. Now there are some tests that you can't automate. And there's some testing that cannot be automated. Mostly the testing that you cannot automate is the testing that requires creative energy. You take a system, you hand it to a bunch of creative people, and you say to those creative people, break it. Find some way to break this system, and they will. Once you challenge someone to break something, they'll find great glee in figuring out some way to break it. And they will think of all manner of interesting ways to break that system. That's the kind of QA that I would like to see. Creative people figuring out interesting ways to break the system. And also QA at the front end of the process, writing the specifications and the tests that must pass. I expect nothing in the system to be fragile. You know that module that always breaks, the one where all the bugs are? Everybody's got one in every system. Wherever there's a bug, oh yeah, it's in that module. Fix that module. I don't expect fragile stuff in our systems. I expect that we will cover for each other. What does this mean? Bob is the database guy. Bob gets sick. Nothing happens on the database. This is unacceptable. If we're working in a team, if Bob gets sick, someone else should be able to step in and take over for what Bob was doing. And whose responsibility is it to make sure that someone can step in and make sure that they can take over for what Bob was doing? It is Bob's responsibility to make sure that someone can cover for him or her. I suppose there are hers named Bob, who, if he goes down, it is your responsibility to make sure that someone can cover for you if you go down. Now, how you're going to achieve this, I don't know. You might decide that some paired programming is necessary or some heavy reviews are necessary. Whatever technique you choose, it's going to have to be good enough so that if you go down, someone can cover for you instantly. A bunch of guys on the field kicking the ball down the field, one of them goes down. The other players change their field position to cover that hole so that they can keep moving the ball down the field. That's how a team works. And that's how you need to work as well. So figure out a way for you to cover for each other. It's a simple expectation, and it's not an unrealistic expectation. I expect honest estimates. What is the most honest estimate you can make? Exactly the right words. I don't know. The most honest estimate is, I don't know, because the answer is, you don't know. How long is it going to take me to do this thing? I don't know. But you do have a little bit more information than that. See, there's two components to an estimate. There's the accuracy and the precision. Now, the I don't know is the right precision. It's just that you haven't been very accurate. So give me some kind of number, right? Like, how long is it going to take you? Well, you know, I think Friday seems like a good number. Here's what I really want. I want 3 numbers. I want the best case, the expected case, and the worst case. I want you to say, well, if everything goes right, and I mean everything, then I might be able to get it done by Wednesday. But things don't usually go right, so probably Friday. You know, but if all hell breaks loose, probably next Friday. Now that's a very honest answer. It's honest both in accuracy and precision. You've given both the expected time, but the boundaries on your lack of knowledge, on your indecision. It's wise to provide that kind of information. And how many of you have done this ever and then had the response, well, that's not good enough. We need to know. What do you do then? You say, I'm sorry you need to know, but that's the best I've got. Well, you got to do better than that. You can't do better than that. Well, there's got to be some way you can improve your estimate. No, there isn't. Oh, come on, you're not being a team player. Actually, I am. I'm giving you the best information I have right now. You're the manager? Manage. Right? And then here comes the word, well, will you at least try? Careful. Careful. It'd be very tempting right now to say, yes, I'll try. You must not say that. The answer is, how dare you imply that I am not trying? I've been trying this whole time. I am still trying. And you're suggesting to me that I'm not trying. I don't have any magic beans in my pocket. I cannot change reality. The numbers are as I've told you. You're going to have to deal with it. I am not going to try. You know, by the way, that you are tempted to say, yes, of course I'll try. And why are you tempted? Because you and I, frankly, did not get into this business because we like working with people. And we're not very good at working with people. So in a confrontation situation where there's somebody in your face going, I need it by Friday, we want to get rid of them. We want them to go away. And if they say, will you at least try? You've got an easy way to make them go away. Yes, I'll try. Now go away. But here's the problem with that. The fact that you have said you will try will not change your behavior at all. There will be no different decision you will make, no different behavior you will use. It will change nothing about the outcome. It was a lie. You told a lie. Because you already are trying. And there's nothing you can do about your current uncertainty. You have to specify it and let the chips fall where they may. You had a question up in the back, and I delayed it as long as I could.
I just want to say that the response we usually get is they only hear it the Wednesday. They don't hear it.
Yes, of course. Right, yeah. You give them the best case, the nominal case, and the worst case. All they hear is the best case. And then they shorten it by 2 days. Right? Because they figure you're padding. Right? This is just a trust issue. Right? And we've had this problem all along where developers will start padding on the back end, and then the managers start taking the padding off on the front end, and it's this constant race to see who the heck has got the most padding or can take it away. You give the range, and you hold to the range, and then you improve the range when you have better knowledge. Because here's the bottom line here. You were hired for your knowledge. And your knowledge gives you the privilege and the responsibility to say no when no is the answer. When the answer is no, we are the only ones who can say that. We're the only ones who know. When someone says, we got to deliver by Friday, and you know that it's not going to happen, We're the only ones who can say that. No, sorry, it's not going to happen on Friday. And it doesn't do any good to say, well, we'll try. Do you remember what happened 2 years ago in October? The American healthcare law demanded that a website be produced by the United States government. And it demanded that this website would be turned on October 1st, 2013. So the law set a date certain for a software system. Now that's insane. You don't set date certains for software systems, especially if they're critical systems, if there's any possible way to avoid it. And they never did have to make it a hard date, but they did. They made it a hard date. Okay, so what happened on October 1st, 2013? They turned it on. And yes, it crashed horribly, and it burned, and it actually burned for several months. And it almost derailed the law. That's how serious it became. Because the furor over the fact that this thing was turned on with great fanfare and then immediately crashed and burned horribly was enough for a lot of people who were tentative on the law to say, no, come on, this is nonsense. Very nearly undid the law. However you feel about the law, a software failure had a profound impact on public policy. Were there some software developers, do you think, that knew that they shouldn't turn that thing on? What were they doing? Sitting under their desks going, oh shit. They're going to turn it on, aren't they? They really shouldn't do that. We are the only ones who can say no, and we were hired for that ability, so we have a responsibility to communicate to our company, by the way, guys, you're insane, this can't happen, don't try. We have that responsibility. I expect continuous aggressive learning. How many languages have you seen go by in the last 30 years? Let me paint just a little landscape on the computer languages for you. Does anybody remember when COBOL was actually popular? That was the 1960s. And then after that we had C. C became popular in the late 60s, early 70s. C++ became popular in the mid-80s. Then Java became popular in about 1995, and C# right after that, because they're really the same language. And then Ruby became popular right around 2005, 2006. And we're seeing another language start up the popularity chain right now, which is, well, JavaScript I probably don't need to mention. There's also things like Clojure and Python and so on. The languages come in waves. And the waves rise, and then they fall. And the career software developer surfs those waves. Right? And you always have to be ready for when the wave starts, your wave starts to go down, you got to be ready so that you can leap onto the next wave. Because you don't want to ride the wave down. It's hard to recover from down there. So you, as software developers, should be learning all the time. Learning a new language every year or two. You should learn new platforms, new operating systems, new frameworks. You should be fiddling around and playing with stuff all the time. Because our industry is one that is constantly changing. And your job will very likely change out from under you in ways that you cannot anticipate if you are not ready for it. When do you do this learning? There's a fundamental truth about being a professional. It is your responsibility to take care of your career. It is not your employer's responsibility to take care of your career. Do not trust your employer with your career. Now, your employer may help with it, might buy you some books, might send you to conferences, You know, who knows what your employer might help you with, and that's fine, that's good. But you must maintain responsibility for your own career. And what that means is that when you give 40 hours a week to your employer to do the best job you can, you are not done. You then go home and you provide another 20 hours or 10 hours or 15 hours for your career. You go home and you fiddle around with a new language, you fiddle around with a new operating system, you fiddle around with a new discipline, you learn something new. And you may say, yes, but I've got a family, I've got commitments. Well, I understand that, believe me, I understand that. But you chose a career that requires grooming and maintenance. And if you do not undertake that, then your career will falter. So either find another career or expect to invest the time. When you go to a doctor, that doctor puts in a hard week at the office, 40 hours a week, seeing patients, doing surgeries at the hospital, doing all kinds of stuff. You kind of hope when he goes home, he cracks open the books and reads the medical journals. Kind of hope he's putting in the time after hours to stay up on what's going on in his field, because his field is changing rapidly. If you ever get sued and you need to hire a lawyer, you know that lawyer is going to be putting in a lot of time in the courtroom and in the office with you. And then you kind of hope he goes home and he cracks the law books and reads on what's going on, because he's got to stay ahead of what's going on in the law. You have to do the same thing too. One last point. And then we'll take a break. And then after the break, we'll have a little informal question and answer session. Mentoring. How many programmers are there in the world? About 50? 50 million. Yeah, it could be 50 million, it could be 100 million, it could be 200 million. It depends on if you count the VBA programmers or not. It's a very large number. How many programmers were there in 1948? 1. Yeah, maybe 5. But big O of 1. Alan Turing was the first real programmer. The first person to write binary code that executed in an electronic computer. And he and his staff of people learned a few things about it. And within 10 years, there were hundreds of computers in the world. By 1955, hundreds of computers in the world, and thousands of programmers. Who were those programmers, those thousands? Well, they were scientists and mathematicians and engineers that were pulled out of other fields. And they were already professionals, and they were generally older, in their 30s and 40s, some in their 50s. By 1955, there were a lot of those, several thousand. 1965, how many computers are in the world? Tens of thousands. Tens of thousands. IBM was already producing 1,000 360s every month. How many programmers were in the world? Hundreds of thousands. We're talking about 20 years later. Hundreds of thousands of programmers in the world. And again, they were drawn out of existing industries, because there were no university programs teaching you to be a programmer. There were no computer science degrees. There were no programming classes. If you wanted to program, you figured it out on your own. You learned. You got a book out. A book on Fortran, or a book on PL1, or COBOL, or basic assembly language, or something like that. You figured it out for yourself, and you better be pretty smart. And these people were drawn out of industry, out of other jobs in industry. They took the best and the brightest, and they said, you're going to program these machines. And these were people who already knew what a job was, already understood business, already understood schedules and deadlines and commitments and all of that stuff. They were already professionals, and they were in our field. And by the way, something like 25 to 30% were women. A huge number of women were programmers in those days. That changed in 1975. When I got my first job as a programmer, it was in 1969. And the place I worked had 25, 30 programmers, I don't remember exactly, but there were, well, about a third of them were women. There was a lot of women there, and I remember that. And these were people in their 30s and 40s. They were mature, professional, understood what they were doing. 10 years later, I worked at a company that had 50 developers, 2 were women. And this curve that I experienced was experienced by the whole industry. In 1975, the computer science degree programs had finally arrived. You could go to college to learn to be a programmer, and the universities started to graduate huge numbers of young men. I don't know why there weren't any women. But the average age of the programmer declined by about 10 years. From 1965 to 1980-ish time frame, the average age of a programmer went from mid-30s to mid-20s. And the number of women in the field dropped from something like 25% down to 2%. Since that time, the number of programmers in the world has doubled every 5 years. Think about it. How do you get to 100 million in 60 years? Right? If you started with 1. Just think of the doubling rate. The number of programmers in the world has doubled every 5 years, and that has a deep significance because it means that half the programmers in the world have less than 5 years experience. And this has always been true, and it will always remain true so long as we keep doubling every 5 years. Half the programmers in the world have less than 5 years experience, which puts our industry in a state of perpetual inexperience. How do we address the fact that all the experience shrinks to insignificance in the face of the massive number of young graduates pouring out of the universities and getting hired? Guys like me, who've been in the field for 50 years, how do I teach the young programmers what to do? Because they come in out of school knowing nothing. They know a little Java, maybe, they know a little something. They arrive on the job and go, what the devil is this? Because university does not prepare you for what's really going on in industry. It seems to me that it would be wise for companies and programmers, frankly, senior programmers, to make sure that new kids coming out of school are not allowed to touch any of the core code for a year or so. Take them on as apprentices, mentor, teach, make sure they're not turned loose on their own. I don't want to see, a bunch of kids thrown in a room and throw in meat and have code come out. It doesn't take a lot of intelligence to produce code. It takes a lot of intelligence and experience to produce well-structured systems with discipline. And that's what we need to inculcate into the younger folks coming out of school now. Because in general, in school, discipline is not a priority. And with that, I believe I will close the talk. Let's take a break. 15 minutes or so. And then we can return here and we can have a session of question and answer. And I'll just take questions as they come at that point. So, break first, then questions. This is weird. All right. Questions? Everybody filed back into the room. Yes.
I have a question regarding the test coverage.
Yes.
You said this green button which you cannot really trust.
Yes.
Because you can never get the 100% coverage. But how about the balance? Like, when it is good enough so we can trust it, kind of.
When is the test suite good enough that you can trust it? This is something that you will have to discover for yourself, because in a legacy environment, there is a very large batch of the code that works. And it really doesn't need any further testing because it's been through the field, it's been through production, It's a decade old, it works. And you'll probably never get that tested, and you don't need to get that tested. So in a legacy environment, the code coverage number is not very significant. Now, how do you deal with a legacy environment? That's an interesting question all by itself. You have a whole bunch of code that is not tested, that was not designed to be testable. How do you even approach getting this button that gives you the green light? How do you approach a test suite that you can trust? And the answer to that is, first of all, don't make a project out of it. Don't decide for the next 3 months, we're going to write a whole bunch of tests. This project will fail. And it will discredit everybody who's been a part of it. It will not produce the tests that you want. And it will probably leave the system in a worse shape than you began. This is what happens whenever you start a project to correct a long-term lack of discipline. The solution is to change attitude. You shift your attitude. You say, from now on, I and every member of my team, whenever we touch this code, we will make it a little bit better. This is the Boy Scout rule I talked about earlier. But when you're making a little bit better, you check out the code, you look at it, you do whatever you have to it, you make it a little bit better. When you make it a little bit better, you are thinking about how you're going to get tests in there. Now, you may be able to write a test. Don't write too many, don't go crazy, write enough tests to satisfy you for that day and then check them in. But you might not be able to write any tests because the code was not designed to be testable. It's too risky to change it to then write tests. So what you'll do then is you will make some small change to make the code approach testability, just a little bit closer. You'll break some coupling, you'll open up some function, you'll change some function argument, something like that. And then you'll check it in and walk away and hope that the next guy can push it a little closer to testing. And then bit by bit, this code will get better and better. What code will get better and better? The code that you're actually touching. There'll be a whole bunch of code in there that you never touch. That already works, you're never going to see it again. Don't go digging around in that stuff. It's the code you're actively manipulating that you want to improve. Secondly, sometimes you'll be asked to add new features. And you'll realize very quickly that there's 2 ways to add the new feature. One way is to smear a bunch of code in the existing legacy, adding if statements and flags and stuff like that so that you can get this new feature in. The other way is to write the new feature in a completely separate module and then couple that module in from the outside into the legacy code. That second way is the harder of the 2, and it's the one you should do because you can test it, you can write all of that code with tests, and you can then factor it into the legacy. So you will have improved the legacy system by doing that. Over a lot of time, the legacy code will get better and better and more tested. And then it becomes a bit like a snowball, because as it gets better and better and more tested, you start to trust the tests more. That allows you to do even more cleanup, which lets you trust the tests even more, which allows you to do more cleanup, and you get this runaway snowball effect. You're kind of hoping that'll happen sometime within a year or so. Next question. Yep.
Test environments, how many stages do you need?
How many?
In your opinion, how many different environments do you need?
Oh, you mean to test your production environment and this customer and that customer and that and this browser and that browser and that browser. The question presumes something that I'm not sure I want to presume, which is that you have entire systems set up for the purpose of testing. You may have that, but that may also not be necessary, because I don't want you on a regular basis to be testing in an offline system. I want you to have broken up your modules to the extent that you can test the individual modules and know that those modules work. And I want that to be your primary mode of testing. And then as a secondary mode of testing, you integrate those modules and test them in a lifelike environment. In that lifelike environment, how many of them do you need? And you need as many as you have production environments outside and in field environments. Now, hopefully you can take one system and alter it so that you can test it in one environment and then the next and the next, so that you're not replicating tons of hardware. But to be safe, you're going to have to test it in each production mode. So you'll have to have some way to swap the system back, change the configuration of the system to test each configuration, each production mode. That means it's going to take some time, and that's one of the reasons we want these tests to run very fast. A good suite of tests should not run for days, or even lots of hours. It should run in minutes. If it's a very, very comprehensive suite of tests that goes all the way through the GUI, it's probably going to run in a couple of hours. I don't want it to run much longer than that, certainly. And for most of the module tests, I want it to be seconds. I don't want that to take a lot of time at all. At which point I should say something about GUIs. Please do not test your business rules through the GUI. Right? A lot of people will buy these systems that allow you to let a tester drive, and the system will record what has happened, and then it will play that back and make sure that what happens on the screen is the same. These systems are a trap. When you're testing business rules, they are a trap. And the reason they're a trap is very simple. UIs change. People change GUIs, and they change GUIs for arbitrary reasons. They don't like the color. They don't like the way the windows flow. Some marketing person will read some new fad on user presentation, and then you'll have to change the order of things on the windows, and all your tests will break. And if all your tests break, then you'll be stuck in the mode of having to redo them, and you're never going to have time to redo them. It's just not going to work, and what you'll do is you'll throw them away. Don't test business rules through the UI. Test business rules through an API that gives you access, the same API that the UI uses. Design your systems so that they are decoupled enough so you can test your business rules through an API. Now, you also have to test the UI, and that's fine. And for those, you can use those systems if you'd like. When you test the UI, decouple from the main system. Replace the back-end business rules with a stub that return canned answers so that all you can test is the UI. You can't test any business rules. And that lets you test the UI independently of the business rules independent of the UI. I could push this even farther and say that you want to test the business rules independent of the database, but we probably don't want to go there just yet. Anybody else? Did I answer your questions? Good? Yes?
If test-driven development is the answer to everything, how come how come people are not learning that in school?
Ooh, what an excellent question. Okay, so if test-driven development is the answer to everything, why aren't people learning this in school? Okay, first of all, it's not the answer to everything. So just so that we're clear on that. But it is a very powerful discipline. Why aren't they learning it in school? Well, some people are. There are some professors that teach test-driven development, but it has not become a general discipline in university. Then again, what has? What discipline of ours has become taught in school? For example, do schools really teach the discipline of source code control systems well? Do they teach students how to deal with check-in and check-out discipline and merging and branch discipline? Do they teach kids in school how to deal with unit testing? Whether it's test-driven development or not, do they even cover the idea of how you test your code and what tests are and what a good test is, what a black box and a white box test is? Some universities do, most do not. Most teach no discipline at all. And the reason behind that is most of the professors have never held a job in industry. Right? they've been academics all their lives and really don't know. They don't know what it's like to actually be a programmer in the real world. So how can they teach it? Software is one of those industries that is ahead of academia. Academia is 20 years behind the industry. And that's not uncommon. When avionics first, not avionics, but aeronautics, aviation was first developed, universities were far behind. They had to be. So who's figuring it all out? You know, well, us, the guys in the field, we're figuring it all out. And then eventually people like us will become college professors, and then we'll take all those disciplines into the university. We're still way too young in industry for that to have happened. So expect the folks coming out of school to be roughly 20 years behind as far as disciplines are concerned. They know some of the new languages. Some. Java. Java's already past the point of its peak popularity. It's already on the decline. Some people think, well, it's a new great language. No, it's a really old language, and it's starting to show how old it is. Anybody else? Yep.
How's your point of view on C# and the .NET framework? On the .NET framework and C#?
Oh, C# and .NET. They're fine. It's a good platform. It's roughly equivalent to Java. And the history of that is fairly interesting. Sun used Java as a way to capture the mindset of programmers back in the early 90s, the mid-90s. They made this decision that the way you sell hardware, remember that Sun was a hardware company. They sold pieces of metal. The way you sell metal most effectively is to win the hearts and minds of programmers. They discovered in the mid-90s that it was programmers who actually decided what hardware got bought. We often underestimate our power, but we were the deciders even then. And so they thought, well, what better way to win the hearts and minds of programmers than to give them a language? And they hunted for a language that they could offer programmers, and at first they thought it would be C++, but then they realized they didn't own that as a monopoly, and it didn't fit with the idea of the internet well. And then this guy who worked for them, his name was James Gosling, waved around this language that he had produced a few years back, which was called Oak, and should have been thrown in the trash. But Sun said, oh, that might be the language, and they promoted it out to the world as the language of the internet. That became Java. Microsoft said, oh, what a good idea. So they produced their own Java compiler. Does anybody remember Visual J++? Right? And then Sun went to Microsoft and said, hey, you can't do that. And Microsoft said, oh, yeah, okay. And they changed a couple of keywords in the case of some function calls, and they called it C#. And the two are virtually identical languages because they were the same language. And then they've kind of divided ever since. .NET's a fine framework. Are you using it? Who's using .NET? And so what IDE could you possibly be using? Okay. One of the problems with going in the Microsoft world is that there's no competition, right? So you're stuck in a world that is not advancing fast enough. Microsoft tries to innovate, and they sometimes do a good job. I like what they did with Link. I like some of the things they've done with C#. On the other hand, I despise Visual Studio. It's a terrible IDE. Are you using ReSharper?
Yes.
Okay, you have to use ReSharper. And it's a very sad story. The idea behind these refactoring and good formatting browsers starts in 2001. And many of us went to Microsoft and said, guys, you've got to do this. You've got to improve your IDE. There's IDEs out there for Java that are just knocking your clock off. And Microsoft kept on saying, oh yes, we'll do that. Oh yes, we'll do that for years and years. And then finally, the guys who made IntelliJ for Java wrote ReSharper. ReSharper makes Visual Studio almost usable. So, that's my thoughts on .NET. Otherwise, it's a fine platform. I don't have any objection to it. Be careful. I think what's going to happen over the next decade or so is we're going to see the platforms survive. The JVM and the CLR will survive. The languages will begin to shift. Java will shift away. It'll get replaced by something, maybe Scala, I kind of doubt it. More likely to be something like JRuby or Clojure or something like that. On the .NET side, you're going to see F# becoming more important. I don't know that that will actually be the language that takes over. It might be something more like, I don't know, Iron Ruby or one of the other variants. But watch what happens in these spaces. The platform will survive. The language will begin to wane. And the reason the platform will survive is just there's too much invested in it. There's an enormous amount of very good stuff at the bottom layers that everybody's going to want to continue to use. Next.
What's your point of view on agile release cycles, or releasing or making your product shippable every 2 to 3 weeks versus true continuous delivery?
If you can do true continuous delivery, you should do true continuous delivery. If your disciplines are so sharp that every time you check things in and your tests pass, you are comfortable deploying, then you should do that. I work on a project like that right now, where we have a suite of tests, and we believe in this suite of tests so much that if the tests pass, we deploy. Now, we haven't made it instant yet. We still go through the manual step of deployment, but the only gate is that the tests pass. And that's a really powerful mode to be working in. There's no delays. Getting to that point is hard. Right? You have to get a suite of tests that is really far down that code coverage line. You're really close to 100%. That little green light lights up, you believe it. You're ready to deploy. Most folks aren't going to be there. They're going to be at a release cycle that is a week or 2 weeks, and that's fine. If you can get there and then keep that going for a few years, then you can start thinking, okay, let's push this, see if we can get to continuous delivery. We got a test suite that's really hot stuff. We're going to be able to just crank it out. That'd be great. It's going to be tough to do with legacy environments because you will probably never get the code coverage you need for it. But in greenfield or brand new projects, probably something you can approach.
Back in the 90s, the developing community, they made a choice to stick with what they call strongly typed language.
Yes.
You think now it's shifting to dynamically typed?
It certainly is. And thank you for bringing that up, because that's a fun story to tell. In the 90s, there was a war fought, and the war was fought between IBM and Sun. And the topic of the war was static typing versus dynamic typing. Static typing are languages like Java, C#, C++, where you must declare the types of your variables before you use them. And the alternate language was Smalltalk. IBM was the champion of Smalltalk. Smalltalk is a dynamically typed language. You do not have to declare the types of your variables at all. A study had been done in the early 90s by Capers-Jones that showed that people using dynamically typed languages could write their systems 5 times faster than people who were using statically typed languages. And people quibbled over whether it was 5 or 3 or 2, but nobody suggested that you could go faster with a statically typed language. Everyone acknowledged that yes, writing in statically typed languages is slower, but it's safer. And that was the argument. We prefer the safety to the speed. Remember this the next time that you are worried about a deadline and somebody's hammering you over a deadline. The entire industry decided to go at least twice as slow for the purpose of safety. IBM lost the war. They had a whole suite of tools all set up for Smalltalk. It was Visual Smalltalk, Visual Age for Smalltalk, and all this really cool stuff. They had it all set up. They lost the war. They abandoned the Smalltalk engine. They went to Java. All the Smalltalk programmers were crushed, and as a language, Smalltalk died. That was the last time Smalltalk had any chance of becoming a significant industrial language, and it never will again, probably. There's always a chance, but I doubt it. The Java people won that war, the C++ people won that war, and that's where it would end, except for a very interesting quirk of history. The Smalltalk programmers were badly burned by this, and they plotted their revenge. They worked at IBM. They decided to release a product that would destroy Sun. They called it Eclipse. Work. The final little bit of irony in that is that the Eclipse engine that generates the JVM code is to this day written in Smalltalk. Next question. Now I'd asked how many of you are doing test-driven development? And I got a pretty good result actually. It was about maybe 10 to 15% of you, which was encouraging. Usually when I go out into the industry at large, that number is about 15 to 20%. 5 years ago, it would have been 5%. 10 years ago, it would have been hardly any. We're on a pretty good growth curve. The discipline is moving through the industry. More and more people are using this as a powerful discipline to get their code written. And once you start using test-driven development, it's very, very difficult to stop because you get really addicted to that little button real fast. And the power that it gives you to change code and to be free of the debugger is a really immense power. How many of you know what it is? What is test-driven development? Let me describe it to you very briefly. This is a discipline that makes no sense to the normal developer. And if you've never heard it described, you will recoil from it in horror because it really doesn't make any sense if you've been a developer for any length of time. I certainly recoiled in horror when I first heard of it in 1999, and it took me several months to wrap my head around this goofy idea. Test-driven development is composed of 3 rules. And the first rule immediately sounds stupid. You cannot write any production code until you have first written a test that fails. Now, what kind of test are you supposed to write if there's no code? Right, so it just makes no sense. But the second law is worse. The second law says you are not allowed to write more of a test than is sufficient to fail. As soon as the test fails, you must stop writing the test. And oh, by the way, not compiling is failing. So the instant the test does not compile, you must stop writing it. Now, you have no code. You write a test, it's not going to compile. You write one line of the test, that line is not going to compile because it's calling something that does not exist. So then you have to switch modes and write the production code that makes that test pass, but that requires one line of code. And that's when the third law kicks in and says, you are not allowed to write more production code than is sufficient to make the currently failing test pass. So now you're stuck in a loop that's maybe 5 minutes long, maybe 30 seconds long, depends on how fast your compiler is and how quick your IDE is and how good your editor is. You might be stuck in this loop every 5 seconds. Line of test, line of code, line of test, line of code. And again, if you're a programmer of any years discipline, this sounds absurd. You'd never be able to write a loop without going back and forth. No if statement could be completed without going back and forth a whole bunch of times. It just feels wrong. It feels like it would be boring and tedious, and it would interrupt your flow of thought and all of this stuff. And it is. It does. All these things, all the things that you predict about it, it does. But there's the other side of the coin. Imagine you got a group of people like you in a room like this, all doing these 3 laws. Pick one of them. Doesn't matter who, doesn't matter when. Everything they were working on executed and passed all its tests within the last minute or so. Everything worked a minute ago. No matter who you picked, no matter when you picked them, everything worked a minute ago. What would your life be like if you were never more than a minute away from seeing everything work? how much debugging do you think you would do? The answer to that is pretty clear. If it all worked a minute ago, there's not a lot of debugging to do. Anybody good at the debugger? You're really good, you know all the hotkeys, step into, step over, step around. You know how you get good at the debugger? You spend a lot of time debugging. I don't want you spending a lot of time debugging. I want your debug skills to wane. I want you to wonder every time you fire up a debugger, and you will from time to time fire up a debugger. But every time you do, I want you looking at it going, okay, how do I do a breakpoint? Oh yeah, click that thing. Step into, is that F8 or F7? I don't want you to know. I want it to be a tool that is so far removed from you that you're not familiar with it. Because if you are following these 3 laws, the amount of time you will spend in a debugger in a year will be measured in minutes. How many of you have integrated a third-party package? So you get a third-party package from a third party, maybe a CD, maybe a zip file. You unpack it. Somewhere in there, there's some code. There's also probably a PDF. The PDF has got an appendix at the back with a bunch of ugly code examples. Where's the first place you go? You want to learn this third-party system. You go to the code examples. You don't want to read what some tech writer wrote. You're going to go to the code examples and read those code examples, and the code examples will explain how to use the system. If there's any mystery, you're going to go to the words after that, but usually there isn't any mystery, because the code examples tell you exactly what you need to know. When you are writing these little unit tests back and forth, what you are writing are the code examples for the entire system. Anybody wants to know how to call an API, there's a suite of tests that calls that API every way it can be called. You want to know how to create some object, there's a suite of tests that creates that object every way it can possibly be created. And these little tests are short little snippets of code. They are a kind of documentation. They are absolutely unambiguous, so formal they execute, they cannot get out of sync with the application. They are the perfect kind of low-level documentation for a programmer to read. You want to read code. Code will tell you the truth. Code is unambiguous. You want to document something so a programmer understands it. You document it in code. That doesn't tell you intent necessarily. It doesn't mean that there is not other kinds of documents you need to write, but the lowest level documents are code. And this little technique makes sure that the entire system is completely documented at the lowest level with little snippets of code that show you the examples of how everything works. How many of you have written unit tests after the fact? Some people do this and they think it's test-driven development. How much fun is it? Now notice the reaction. That was an interesting reaction. Of course it's not fun. Right? It's not fun to write unit tests after the fact. Why isn't it? Simple answer. You already know it works. You've tested it manually. Right? You've seen it with your eyes. You know it works. And now some process guy said, yeah, but you're supposed to write tests. And you kind of go, oh, well, all right, I'll write some tests. And it feels like make work. It feels like busy work. It's bothersome. But you go ahead and you do it. All right, I'll write a test here. All right, yeah, all right, I'll test it. Okay. Oh, that one's hard to test. Inevitably, you come across the function that's hard to test. It's hard to test because you hadn't designed it to be testable. And now you face a dilemma. I got to change the design. Well, I saw it work. Never mind. And you walk away. And you leave a hole in the test suite. And if you're leaving holes in the test suite, everybody else is leaving holes in the test suite. And that means that when that little light turns green, you all kind of nod and go, yeah, I know. If you write the test first, that can't happen. If you write the test first of all, it's fun. Because you haven't seen the code work yet. And every little test is this little proof that you can still write code that works. You write a little test, it fails, and then you go over here and you make it pass. Yeah! Another failure. Yeah! And you get this little charge all the time. Yes, I can still write code that works. I'm still a god. Second, you cannot write the function that's hard to test. Because you wrote the test first. When you write the test first, you must design everything to be testable. You don't have any choice about it. your first thought about the production code is, how do I make it testable? And there's another word for testable, decouple. That's how you make something testable, you decouple it. So the very act of writing the test first forces you into this heavily decoupled mode. You will decouple like crazy because of this, and that will simply improve the design of your system. You just get a better design. There's all these little side benefits. You aren't going to be in a debugger for the rest of your life. That will probably make you go a lot faster. You'll have all this low-level documentation. That'll probably make you go a lot faster. You're going to design the system better. It's fun. That'll probably make you go a lot faster. All these things will probably make you go a lot faster. And they more than make up for this funny business of writing the test first and all that stuff that you initially thought it'd be slow and tedious and boring. More than makes up for that. And then, after all of that, you get this suite of tests that you trust with your life. And that suite of tests that you trust with your life solves so many other problems. You can clean the code fearlessly. Clean the code. You can manipulate the code. You can twist it any way you want. How many of you believe that design is really important? Got to get the design right. Right? Books have been published about this. Right? We got to get the design right. Why? Because we have to keep the code flexible and maintainable. Nothing makes code more flexible and maintainable than a suite of tests, by a huge order of magnitude. You give me an application that is perfectly designed, beautifully designed, but there's no tests, I'll be afraid to modify it. I'll be afraid to touch it. It will rot. You give me an application that is badly designed, but it has a comprehensive suite of tests, I will improve the design. I will gradually make that design better and better, fearlessly, because I have that suite of tests. The suite of tests means much more than a good design. So to the extent that you are considering design important, multiply that by 10 and make your tests important. Yes, sir?
What do you mean by a beautifully designed system? When a design is beautiful?
What I meant was a well-designed system in terms of principles of object-oriented design and separation of concerns, a system that is easy to change because of its design. Yes?
So TDD is one of those things in the industry that there's still a lot of debate about, right? In exactly how does it look?
Yes.
I haven't heard any sane people argue against automatic testing or everybody wants to run with green light, but exactly how does the code look afterwards? And I know you probably follow the debate from David Heinemann and Hansen's the test-infused design damage, which is kind of stuff I want to talk about here.
Yes.
That obviously we want automatic testing, but if the way you induce this sort of removes your ability to read the code and sort of
I know the argument very well.
Yeah.
I know David.
So how do you see that argument?
Well, here's how I see that argument. David Hannemeyer-Hansen, that's who you're talking about,
Yes.
is the author of a framework called Rails. Rails is the framework in which Ruby applications are often developed. And Rails gives you a very powerful way to get an application up and running very quickly. If you want to do anything extra with the application, you will find Rails starting to impede you, right, and getting in your way. And the more interesting stuff you want to do with the application, the more Rails gets in your way. And why does this happen in Rails? Because the way David designed it was to force you to couple very strongly to the framework. If you try to decouple from the framework, David calls this test-induced design damage. Because from David's point of view, if you decouple from Rails, you are damaging your design. Why would he think that? Because it's his framework. Here's the thing about frameworks, and you will find this to be consistent about every framework author. These people are not bad people, they're good people. And they offer their code to the world for free and pat them on the back and say, thanks bunch, that's great, good. But every framework author wants you to couple to their code. They want you to derive from their base classes. They want you to intertwine your code with theirs. Because somewhere in the back of their mind, they know that once you've done that, you can never get away. A good software developer looks at frameworks and says, somehow this framework is going to screw me. And so you look at frameworks very carefully and you think, okay, I want to use it because it's powerful, but I am not going to take my family jewels, the business rules that make my company money. I'm not going to infuse those business rules with that framework. I'm going to decouple from that framework to keep my business rules safe. Because I don't know if I'm going to be with that framework forever. I may want to change it. A good software developer looks at frameworks with a jaded eye. They're going to hurt you. So they're going to help you. They're also going to hurt you. And you never hear the documents tell you how they're going to hurt you. They do tell you how they're going to help you. Now, that's not to say they're evil or bad. It's just the nature of any kind of framework. Any kind of framework must be less than perfectly general and must at some point cause you pain. It just will happen. And so you, as a general rule, keep yourself at arm's length from frameworks. Anybody doing dependency injection? Using what, Spring or something else?
Structure manager.
Yeah, okay. So do these tools want you to instrument your business rules with little twiddly things, annotations or attributes or something? A lot of them will do that. The Spring framework, for example, wants you to put @auto-wired in all of your business rules. They want you to smear the framework throughout your business rules. I would suggest you not do that. I would find a better way to decouple from your dependency injector. How much do you inject in with your dependency injector? Are you injecting everything? Probably shouldn't be. Dependency injection is a lovely idea, but it's not the kind of thing where you want to inject thousands of objects into your system. You probably want to inject a few strategic strategies and factories and you want to inject them in a safe part of your code and then pass them around to the rest of your code in normal ways. Just general principles. You keep yourself safe from these frameworks.
Sorry to interrupt, but I'm looking at
Oh, sorry.
I'm sorry to have to stop this.
Oh, okay, sorry. Well, I guess we're done. Thanks.